Okay, in this lecture, I want to talk about different ways of handling passing parameters to functions. We'll see how this works in Python, C, and Scala, and in Lattice as well. But it's an important thing for you to understand because it sort of unveils a lot of hidden little errors that we tend to have as programmers when we don't understand quite exactly how our language handles parameter passing. So you can find this notebook under the name callingconventions.ipynb in the weekly readings, and you can either follow along or check this out later. So let's start with a little bit of Scala. Right, so we have this function foo. It takes in an integer x, returns an integer. And if x is odd, then we multiply it by 3 and add 1, otherwise we divide by 2. So we're going to make a val z equal to 10, and then we're going to call foo on z. And it does what we expect it to do, right? 10 is or even, so we divide by 2 and return 5. So that makes a lot of sense. Okay, now we're going to look at another Scala program. One where bar, what does bar do? It takes in an int x, returns an int, and first it reassigns x to 25, and then multiplies x by 2 and returns that. And we're going to pass it a variable z, right? So it's mutable. We're going to set that to be initially 12, and then we're going to call bar on z. And you'd think that naturally we should be able to reassign z, right, since it's mutable, to 25 and return this. We actually get an error. We see that it's a reassignment to val error, which means that x actually isn't mutable. It's a val, right? It's on a var. So what happened? Well, this is because Scala passes by value. So something basic like an integer or any of the built-in types, what it does is it fully evaluates whatever, say, z is here, and replaces it with that value. So z in this case is equal to 12. So when we pass it into bar, we're actually calling bar on 12 and not the variable z or any sort of reference to that z. We're passing by value. We just passed the value in. Same thing happened up here, but we didn't have so much of an issue because z was a value. So once we fully evaluate it anyway, we still get a value back. So we didn't have this issue of a var turning into a val. But this is how Scala tends to handle basic types, right? So it fully evaluates the argument before we pass that value into the function. So let's look at another version of this. And this time what I've done is I've wrapped the integer in, or the variable, in a case class called wrapper, right? So all I've done is made a basic class here called wrapper that has a variable x in it, and now bar takes a wrapper in, and it assigns the wrapper's x, right, the member variable there, x, to be 25, and then returns 2 times c.x. And we see, so we'll have a val w be a wrapper with 0, right? So we're just going to start out with 0, and then we will call bar on w. And what do we get? Well, before the call, w.x was 0, and after the call, w.x is 25. So this actually did exactly what we wanted it to do. And we can see down here that the return call from bar is 50. Right, so this is exactly what we sort of thought maybe Scala program A would do. But yeah, what happened? Well, what happened is that Scala for user-built classes will pass by reference. Or maybe a better way to say that is that when I evaluate w, right, to get its value out, what is the value of a class? Well, it's a reference to its location in memory. And so when we pass w to bar, we're actually passing a reference to the memory cell that contains all of wrapper's data. And since the data in that memory location is variable, we can actually change it. We can't change the location of that memory, right? That would give us one of these reassignment to val issues. But because the stuff inside of the memory location is mutable, we can mutate that. So this might feel a little weird, maybe like we're getting around an issue with this, right? To be able to sort of pass by reference when we're actually passing by value. But it's, yeah, that is kind of what we're doing, right? But it also makes a lot of straightforward sense that essentially a user build class, when we evaluate it, when we figure out what its value is a reference as opposed to something like an integer whose value is a number. And it being a reference lets us be able to access whatever is at that memory location. So we can also do this in Lattice, right? So we can do call by value is the way that we've been doing things in Lattice already, right? Here's a little Lattice program. We have x is 10, and we'll make a function f that takes in a z and multiplies z by 2 in f of x plus 20. And so how did we write up our semantics for Lattice for function calls, right? Well, what we do first is we fully evaluate the expression that is going to be the parameter, right? So we fully evaluate x plus 20 and get 30. And then we pass that in, we bind that to z in the local environment of our function body. So z is bound to 30. Right? It's not bound to x plus 20. It's bound to whatever x plus 20 evaluated to before we got to the body of the function. So this should return, well, 60 as we would expect. Let's look at another Lattice program. Right? So let bar be a function of x, where we let dummy1 be a sine ref of x to 25 and 2 times d ref of x, and let z be a new ref of 12 in bar of z. All right, so here we're using the explicit references in Lattice. And what are we doing? All right, so we made a function on x. It's going to assign x. It looks like x should be a reference, right? Because we're going to assign to whatever x points to 25, and then we're going to multiply 2 times whatever the value is at the location of x. So that means that, yeah, whatever we pass the bar should be a reference. We're going to let z be a new ref to 12, right? So what does that do? New ref looks in the memory store, looks for the first place that's empty, and then puts 12 there and returns a reference to that cell. So for instance, probably it's going to be reference 0 since there's nothing else in our store right now. So z evaluates to reference 0 when we fully evaluate z. So bar's parameter here is reference of 0. Right, so now we can walk through it and we can see that, okay, so when we call bar, we're going to bind x to reference of 0. And then this line, let dummy1 be assign ref x25. Right, that's a way to say reference 0. We're going to assign whatever is in location 0 to be 25. And then we're going to deref the reference of 0. Right, that's going to give us back that 25, and we'll multiply it by 2. So we get 50 from this. So we can do, with our explicit references, we can do pass by reference, right? And in our normal Lattice land, we're doing pass by value. And we sort of see that they're essentially the same, right? It just depends on whether or not you include references as a value or not in your language. But yeah, you can see this allows us to do side effects that affect our variables outside of the function body itself. So yeah, Scala always does call by value by default. There's a couple of other types of calling conventions Scala can do called call by name and call by need. Typically for things like iterators where you want to make sure that you don't fully expand an iterator, right? The idea of iterators is we might want to have a lazy feed where we have our data, we only pick up one at a time as opposed to taking up all of our memory by evaluating all of, say, a list, right? But those are special syntax and special needs that you need to go through. So you can look that up on your own, and we're going to just sort of ignore those and focus on the call by value. So let's go back to our original program, right? Program A, right? We have bar takes in an x, it tries to assign x to 25, and it tries to multiply 2 by x and return that. And we pass it in a variable z. So it fails for 2 reasons, right? Parameters of functions in Scala are always vals, so immutable. All right, so whatever we pass to a variable, it rebinds it to a val, the value to a val. So we can't bind x to anything else. And further, yeah, as I mentioned, z gets fully evaluated. So even though it's a variable, we see what is z's value, and then we just pass that value in to bar. So in Python, this would actually be fine, but still not quite work. Right, so here's a Python version, right? We have def bar, x equals 25, and return 2 times x. And we let z be 12. We're going to run bar on z and let that return be z or t. And let's print this out. And we'll see that t ends up printing out as 50, while z stays as 12. So in other words, in Python, we can function parameters are variables, so we can change them inside of the function. However, it's still a call by value, right? So when we pass z to bar, we're actually passing the value 12 to bar, which we bind to x. It's just, this is a little different than Scala because we're allowed to rename x or rebind x to something else. Because in Python, everything defaults to a variable instead of a val. But doing this rebinding doesn't actually change our original variable z, right, outside of the function. It sort of changes what the local pointer is and not what the global variable is. So that's an interesting little twist for Python. And in Lettuce, we can sort of do a similar thing with implicit refs. Right, so here let bar be a function on x. Right, we're going to assign x to 25 in 2 times x. And then we're going to let var z equal 12 in bar of z. Right, so this is Lettuce with implicit references. So let's step through this as we go. So we let var z equal 12. That's going to essentially assign a new ref to z, and we're going to put 12 into that memory location. And then we're going to call bar of z. And remember what happens with our implicit references. Anytime I see this z floating around, I'm going to implicitly dereference it. So I get the value back out. I'm going to get 12 out. Right? And then I'm going to pop it in here, and I'll see assign bar x equal to 25. And that should be fine, right? The issue is that we'll have automatically deref z. So when we pass z into bar, we get 12, and x is bound to 12. So we'll get a failure when we try to assign var to 12, right? Not to a memory location or a reference, but just 12. And we can't do that. So the issue with our implicit references is that we automatically dereference when we try to pass this in, right? So this doesn't quite work the same as we saw with our other example where we actually passed in with the explicit references, where we pass in a reference to the location. All right, so this is similar to this program B, right? Where the idea is that we don't actually implicitly deref our val w, right? When we fully evaluate w to figure out what its value is, it is actually just a reference to a memory location. And so in Scala, when we do this sort of process of making a class, right, we're passing in a full reference, much like that first example with the explicit, right, this example with the implicit, or sorry, this one, right? Wait, there we go. It's very similar to this style, right, where z is a reference to some memory location. So this is essentially what's going on with the wrapper example. So yeah, why does this happen, right? And in Scala, it makes sense because we really want to, we can even see here, right, inside bar, pass the value w equals this Ammonite session helper wrapper, and this is a memory location, right? So the idea here is just anytime we have a class in Scala, it really sees it as a location as a pointer to a memory location. And this doesn't quite happen when you do things like in C or C++. So here's an example in C, or actually C++, where we have a big struct, right? So we've just bound a bunch of data together, and we have a constructor function here, right? In C++, a struct is basically just a fully public class. So we've just bound an integer, a character, and a large vector together into this big struct. And then we're going to make a function foo that takes in a big data struct and then rebinds a bunch of those values, returns 0. And then in our int main, what we're going to do is we're going to make a new big data struct and call foo on this new BDS or big data struct BDS. And so how does C++ handle this? Well, we're going to actually get a full call by value. So what it does is it makes an entire copy of BDS into a completely new struct, and then we call foo on that. So when we bind BDS, we actually fully evaluate it out. We don't just get a reference like we do in Scala. And so foo will then modify this BDS 0, but it's not going to modify the original BDS that we created. And that's because we're truly passing by value, right? We're fully evaluating this out, making a copy, and then passing the copy of all of that data. This isn't necessarily, I mean, this might be more direct as to what we would want to say with call by value, as opposed to the sort of half thing that we see in Scala and Python. But yeah, it doesn't let us sort of maybe have the side effects that we would want. So what we can do, right, and C does this, and C++ lets us do this, which is we can also call by reference if we want, right? So we don't have to just call by value, that's the default, but we can call by reference. And call by reference is really comes from Fortran. It's traditionally the way that Fortran handled passing values into subroutines. So here's a little Fortran swap function, right? That'll take in an A and B, which are 45 and 55, and then it's going to bind the reference that A points to X and the reference that B points to Y. And so when we do this swap routine, we actually do swap A and B. And that's because when we do these evaluations here, we don't actually evaluate it. We just pass in the reference to the memory that A points to and that B points to. And we can do this also in C++ by having this ampersand symbol. So the idea here is that the ampersand tells us that this is actually a reference to some value X, and this is a reference to some value Y. So we can have the exact same functionality as in this Fortran code, where we can basically make A and B be 45 and 55, and then we can swap them and actually have the proper swap happen. Right, so it lets you have a couple of nice things. It lets you do return parameters, right? It lets you basically do stuff and change stuff in place, and then return other values that are more important per se. And also, it doesn't require you to make full deep copies of large data structures, right? That's sort of the reason Scala doesn't do this automatically for user-built classes, because the idea is that those classes might be very complex and have high overhead or a high overhead for changing things, or for making a full copy. So often we'll want to be able to just reference that local thing. And so, yeah, we can change our original C++ function, right, this foo, to just be with an ampersand. And what that'll do is it'll make it a call by reference. So now we'll actually modify the original big data struct that we had before. And so if we want, we can actually even add this functionality into Lettuce. This is beyond what you'll be tested on and stuff in the class, but it's still useful to kind of check out, where we add this new syntax with the ampersand, just like in C or C++, that says that when I'm passing this in, pass me a reference and don't actually deref automatically. All right, so the idea is that we're doing Lettuce with implicit references, and we also want to be able to say, hey, don't implicitly dereference that when you pass it to my function, right? Keep it as a reference. So we see that exactly here. All right, we're going to let var of y be 15, and then we'll pass y into bar and call that z, and then we'll see what y is. And what is bar? Bar is a function that takes in a reference to some that we'll call x, and then we'll assign whatever is in that reference of x to be, and this is interesting, right? X plus x. So x was a reference to a memory location, and we have, on the one hand, we're assigning that memory location x plus x. And remember, this is in our implicit reference lattice. So when we see x plus x, we actually automatically dereference x and get the value out that's at that memory store and add that value to itself, right? And then we pop it back into the memory store that's pointed to by x. And likewise, we automatically dereference x for this x plus 20. And so this is cool, I think. You'll see at the whole bottom half of this notebook is the all of the lattice syntax and semantics for adding this ampersand in so that we can do call by reference in lattice. So if you have the time, I recommend just walking through this, checking it out. I'm not going to do that here because it's just, more code detail. But I hope you found this interesting. Understanding and being able to manipulate call by reference versus call by value is really important as a programmer, right? Just to know how does your language actually work. And to know that when you're passing something through, will it actually work properly? You might have seen this in the algorithms course or some of your other courses, trying to write up a function that does something in place only to find out that your changes aren't propagated back. Yeah, and that's all for this lecture.